Thank you very much. So I'm a last-minute replacement for Irina. I hope she will recover soon. So the organizers... Okay, so great that she's back in the audience. Still, I'm taking this part in the schedule. So thanks to the organizers for, well, in the first place, organizing this thing. It has been very nice so far. So I would also like to thank the participants and the previous speakers. So I got this offer to step in. So I looked up an old presentation, and that's the one that's now on the screen. So of course I had to change some things here because you see, this is not exactly what we're doing now. So I did this, and now it's the talk for today. So I'm not really very well prepared. That's what I want to say by showing this. So please, if it goes wrong, don't blame me too much. It has some benefits to step in at the last moment because you don't really have stress beforehand. You just go there relaxed, and only like today I'm feeling a bit stressed. Okay, so let me also talk about the pi. The pi was there because this talk was on the occasion of the 60th birthday of Geuver. But I think there's again a birthday coming up, 60 plus epsilon for core. So I think the pi is still a very appropriate thing to show there. I have to give credits to Dr. Utker, who makes these kind of pies, and also the picture is due to Dr. Utker. Dr. Utker was actually quite a significant scientist. So he made a lot of breakthroughs in the art of preparing pies. So for instance, he invented baking powder, which I think quite an influential thing. So this is, now let's go to the contents. So this is joined with Wiep Bosma. Maybe I should say a few more things about Core. So Core actually was my co-promoter a while ago. But already before that, I met Core because he was the lecturer for some course, I think maybe stochastic processes for second-year mathematics students. And a thing that really impressed me a lot was that Core can do something... Okay, I'm not allowed to tell this. So let me then tell something else about Core. So Core had an office. And if you enter this office, I still, up to this day, don't really know if there is a desk there. Because when you enter, you see this huge pile of paper, which is in principle big enough to hide a table under it, but you never know if the table is actually there. So it's actually fun. So if you ever have the opportunity to visit Core in his office, you should definitely do so. It's a nice experience. Also because Core is, of course, a nice person to talk to. Okay, now let's really go to the contents. So the Fibonacci sequence we have seen already several times this week, also in the talk before the break, although that was with ones and twos, but that doesn't really matter. So you start with 0, and you substitute 0 by 0, 1, and if you see a 1, you substitute it by 0, and you iterate. So you get like this thing, and you continue like that indefinitely. And well, a reason why this could be called Fibonacci sequence is if you look at the lengths of these iterates, you see that if you take the k plus first image of 0, well, that's the first and then k more times. The first image of 0 is 0, 1, which by definition you can write as this concatenation. And then you see that fk of 1 is actually, well, 1 goes to 0, so it's the fk minus 1 of 0. And now you see k plus 1 equality k and k minus 1. So that's exactly the Fibonacci recursion. So also for the lengths, it is true that the length of some iterate is equal to the sum of the lengths of the two previous ones. And we will use that later. So the limit is well defined. That's also an important remark because you see the initial part is not changing, so you can just continue this forever. 0, 1 is the alphabet. So yeah, maybe I should say this talk a year ago was for an audience that had no idea about this kind of thing, right? So maybe, yeah, this is all sliced cake for most of you. So this is the Fibonacci sequence that you get in the end, and we call this a pure morphic sequence. So any sequence that is generated by this kind of substitution is a pure morphic sequence. Now you can make this slightly more general. So this again is a morphism, which gives a pure morphic sequence, but now we introduce the notion of a coding. So that means there is an additional map from the alphabet, in this case 0, 1, 2, to some other alphabet, in this case 0, 1, and you just map the letters of your original alphabet to this other alphabet. Map, and what you get is something like this. Just a projection on another alphabet. So this is what we call a morphic sequence. The pure morphic is only substitution, and if you add this coding, it is morphic sequence. And now it's also important to know that the same sequence might have different morphisms that generate it. For instance, if we have this Fibonacci sequence, which is generated by 0 goes to, what was it? 0, 1. 1 goes to 0. The same thing is generated by 0 goes to 0, 1, 0, and 1 goes to 0, 1. And this is basically the square of the original map. And it's clear that the square generates the same sequence. Name tag, but by now you know. So in general, there are many ways to generate the same morphic sequence. So we will be interested in its complexity. And by complexity, we just mean you look at each image and you sum all the lengths. So for Fibonacci, that's equal to 3. And that's basically the minimum that you can have for something interesting, because you need at least alphabet size 2, and you need at least one of the images to have length 2, otherwise you don't have an infinite sequence. So this is, in a sense, the smallest example. And for a general morphic sequence, you can talk about its complexity as well, but just looking at all possible morphisms that generate the sequence, so that's what I write here, and you take the minimum of that. So for instance, for the Fibonacci sequence, you see we have different ways to do it. So this morphism has complexity 3, this one has 5. There might be many more morphisms doing the same thing, but the smallest has size 3. So the complexity is 3 of this sequence. Okay, then there's Dekking. Dekking is also an important person in my life. He was my promoter. And he said in 1994, well, he said something else, but this is a consequence of a more general theorem. So if you have a morphic sequence and you take some arithmetic subsequence of it, it's again a morphic sequence. So let's take as an example again the Fibonacci sequence, but now I only look at the numbers at places, indices of the form 4n plus 2. So that's a subsequence, which at first sight you might think, okay, this is 0, 1, 0, 1, 0, 1, 0, 1, 0, 1 indefinitely. Well, that's not true. A bit more interesting than that. And the question we will try to answer today is, okay, Dekking says it is a morphic sequence, so can we find a morphism that actually generates this thing? And can we say something about the complexity of this sequence? So what is the smallest morphism that will generate this arithmetic subsequence? That's the question we ask today. Because that Dekking does not really give something explicit, at least not a construction. So the idea that we had in mind was the following. Well, we want in this example to have an arithmetic subsequence with step size 4. So we just split the sequence in blocks of length 4. And then each block will be a letter in a new alphabet. Right? So the letters in the alphabet will be all possible blocks of length 4 in the Fibonacci sequence. So there are 5 of them. And then sigma looks like, well, if you encode these blocks in this way, you get another sequence which looks like this. And then, of course, you can map each of those letters A0, A1, and so on to the corresponding digit that we're interested in. Right? So you have a coding from A, so from this set, to 0, 1, which just maps each of those letters to the third bit. So that gives you the coding. What is, of course, still missing is the morphism. So now we have an idea, but we still need a morphism that generates this sequence, a pure morphism that makes this. So a morphism on the alphabet is 0, A1, A2, A3, A4. Now one idea that you could try is, okay, well, A0 just corresponds to this block of length 4. We know what a morphism F is doing on this block, so we just try to look at the image and we try to translate this back into the alphabet of blocks of length 4, but that fails, right? Because this cannot be decomposed in blocks of length 4. This is not a valid letter. So that's a problem, and we solve it by instead, that's not really a solution to this problem. They're falling asleep. This was not supposed to happen. Is there technical assistance in the room?
Is this due to your file, or is it?
The file in the morning was still fine.
I'm afraid I'm not. This is your computer.
Yeah, so maybe I can reopen it somewhere. I was a bit early. Okay, so thank you for waiting till the end of this interruption. Let's see where we are. Yeah, so the problem is that this is not an allowed letter. So we look instead at powers of F, and we hope that maybe if we take a power, then we get images which are composed of blocks of length 4. So here you see I take the 6th power of F, and for some reason we get lengths which are all divisible by 4. You can check that this indeed is the case. So that means that those images of the 6th power, they can be written as words over A. So instead of using the original morphism, we just use the 6th power, and we apply this idea to the 6th power. And then it all works. And the complexity of the corresponding morphism is, well, you just take the sum of the lengths of the images. So that's what I do here in the numerator. But I'm interested in the lengths in the new alphabet, right? So these are the lengths in the 0-1 alphabet, but I have to divide by 4 because I'm interested in how many letters in the new alphabet this is. So that's 89. That's the complexity of the morphism that generates this particular arithmetic subsequence. Now you could ask, okay, well, it works for this choice of M. Does it also work for other M? What is actually the reason that it works? And it has to do with, well, this is the Fibonacci numbers. It has to do with the fact that this image has a length which is divisible by 4. And if you write out what this image actually is, you see that, well, it consists of 4 terms. Each of the terms is a Fibonacci number, and f8 you can write it as f6 plus f7. So you see it's 4 times f7 and 3 times f6. So if f6 is divisible by 4, then the whole thing is divisible by 4. And that's also true if the numbers of 1s and 0s is different. For instance, the word 1001 would, I think, give you a 2 here instead of a 3. But if f6 is divisible by 4, it's still fine. So you look for a Fibonacci number which is divisible by 4, and if you have that, there is a power for which it works. Yeah, so in general, if you want to do this for an arithmetic subsequence with step size m, you need some Fibonacci number, which is divisible by m. Okay, well, here you see a picture. On the horizontal axis is just, well, the natural numbers. And on the vertical axis, you see, well, you should mainly look at the blue points. Where is the first 0 of Fn modulo m? And this m is what is on the horizontal axis. So on the vertical axis, you see how far in the Fibonacci sequence you should go to find something which is divisible by m. And you see that it seems quite wild. It's going up and down quite a bit. But also there seems to be sort of a linear upper bound for the blue points. And it is actually true that you will never go above this line, which I think is 2 times m. So if you look for the first Fibonacci number divisible by m, you never have to go beyond index 2m. So that's good news. Actually, it's not so hard to see that there always is a Fibonacci number which is divisible by m for each integer m, because if you look at the Fibonacci sequence modulo m, this is periodic. And it starts with a 0, so there should be another 0 somewhere. Well, this gives you a worse bound than this argument here of argument than what is can be seen in this picture. Right? So now let's go back to this complexity thing. So in the example, if you want to count what is the complexity, you look at the size of the alphabet, so the number of blocks length m, which is in general m plus 1. So that's the factor complexity of the Fibonacci word. And you look at the length of those images, and you see for the 6th power, as we computed before, it is this number, which can easily be upper bounded by 4 times f8, and in general, it's just Fibonacci number with index, the power that you have here, plus 2. And you see, if you look at the lengths of the images in the new alphabet, you again have this division by 4 that we had before. So the 4 cancels, and you see that the length of the image in the new alphabet is at most f8 for all letters in the alphabet. So the complexity is then the sum of those things. It's upper bounded by the size of the alphabet times the corresponding Fibonacci number. And you can generalize this easily. So in general, the number of different blocks of length m is m plus 1. And the image is again upper bounded by a Fibonacci number, where this is the index of the first Fibonacci number divisible by m. And then you get this plus 2 that was also appearing. So this gives you an upper bound on the complexity, which is given in this theorem. So the complexity of this arithmetic subsequence is at most m plus 1 times this corresponding Fibonacci number. And if you look at this in a table, you see it also is not really monotonic. And that has to do with the fact that these places where you find the zeros modulo m behave not very regularly. I made some of them red, and those correspond exactly to the Fibonacci numbers here. Because if you take, for instance, 8, then the first Fibonacci number divisible by 8 is, of course, 8 itself. So for the Fibonacci numbers itself, it is easy to find those zeros modulo m. But for some cases, for instance, for multiples of 30, it's quite bad. So I think this probably is then really the F2 here, I guess, because an upper bound for the Zm was 2 times m, and the worst case is, for instance, for m is 30. Okay, some remarks. Actually, the complexity of our construction is slightly less than this, because remember, I upper bounded it here in this way. And of course, if you plug in what is here instead of 4 times f8, then you get something slightly better, but it's not really much. Second remark is, well, the true complexity might be much smaller. And in fact, it is. So this is open. I think it's still open what the true complexity is, although we made some progress in the last year or so. So I think now we can prove that it's at most a polynomial. We are still working out the details. So this here is, of course, exponential in M. So we reduce that to polynomial, but I think finding really the true complexity is probably quite hard. And we also want to extend it to other morphic sequences. And I think we have some ideas. Our new approach probably works more generally than the Fibonacci example. So what you can do for small examples is you can just run a computer program and try to find the best morphism that generates the sequence you're looking for. We did that for, or maybe I should say, we actually did that for step size 2, and then you find that the even subsequence can be generated by a morphism of complexity 8, the odd one by a morphism of complexity 9, and compared to the construction we have, that was 13. So there is really a difference between the truth and the construction that we have. A problem is, well, you can use brute force to find a candidate, but then you also need to prove that this candidate actually is doing the right thing. So that there still is some work to do there. I think walnut is probably the way to solve this. I think I'm about done. Yeah, so I don't remember what the time slot was that was planned for the original talk a year ago, but probably it was less than half an hour. So that's no problem. It would have been worse if I needed twice the amount that was allocated to me. So I think I just stop here, and there's probably some time for questions.